Hello and welcome to another video. In this video we're going to be working on design, add, and search words data structure. So you want to design a data structure that supports adding new words and finding if a string matches any previously added string, implement the class, we need to have a constructor, and then we need to add a word, and then we need to actually search for the word. And there is a caveat here though, is that there can be a dot where the dot can be any character, and I believe they do say that like there can only be one dot or something, because if there's a lot of dots this adds a lot of complexity. But let's go through the example. So we have input word dictionary, which just makes the actual dictionary. We can add word bad, add word dad, mad. Then we search for pad, and there is no pad. Then we search for bad, there is a bad. Actually, yeah, there's a bad. So let's actually go through these, right? So we add bad, we add dad, we add mad. So we search for pad, there is no pad. Then we search for bad, there is a bad. Then we search for dot add. So dot add just means there can be any word in here as long as there's a word that this character can be replaced by. Then we should return true. And there are words, right? And you only need one of them. So like if we replace this dot with a B, that is a valid word. So that should return true. And similarly, I guess, yeah, there can be more than one dot. So if we have B dot dot, there just has to be any word that starts with B. And so here we have bad, so that would work, right? Essentially dot is like, it can be any character, and as long as anything can match in here, it would return true. So this would work because you can replace these dots with bad. And so this is kind of the tricky part of this problem, is what do we do with these dots? So before we begin, you should be familiar with a try data structure, and if you haven't, just go back to making a try video that I made. I think this was like the last TypeScript video. But I'm not going to spend too much time explaining what a try is and stuff. But essentially, we're going to be using tries here. Again, it's actually pretty funny. I think I've used tries like 4 times or something in the Blind 75, and it's a pretty rare data structure. So we're going to make a try here in this word dictionary. And essentially, our try is going to be the root. Okay, so we're going to make a try in our word dictionary, and we're actually going to use it as part of the word dictionary. So this word dictionary class is going to have a try, and that will be the root. So we're going to have a root, and we are going to draw that root with a dot. And essentially, every time we input a word, let's kind of see what that's going to look like. So like how try normally works. We're going to save this root, but let's say we're trying to put in all these words, right? So like bad. So putting in bad, as we did for the try before, we go letter by letter and we go down, right? So we check, is B in our try? No, it's not. So for key B, we're going to make another try. And then we are going to go to the next letter, putting in A. For key A, we're going to make another try. And for key D, we're going to make another try. Maybe let's actually draw these tries in another color. So these dots represent tries, and these lines represent, nesting of the tries. So these are all tries, and essentially now that this is the end of the word, we'll mark it maybe like blue or something as the end of a try. So this try is a word right here, and the rest of them aren't. And let's say now we try to put in the other words. So we put in bad. Now let's try to put in dad. So similarly, we're going to check for dad. Is a D in here? No, it's not. So this is going to be a brand new try. So D, A, D, like this. And once again, we're going to show these as green for tries. And we're going to mark this one blue by representing the end of a word. Then we put in mad. So for mad, we're going to check is M in here? No, it's not. So mad is going to be another try. So maybe just draw it this way or something. M, A, D. There we go. And these are going to be like this. And this last one is going to be like this, right? So we have mad, we have bad, and we have dad in our try. Okay, now let's try to search. So for something like pad, it would be really easy, right? essentially what's going to happen here for the search word. We are just going to try to search, and here it's pretty straightforward. Like, we just start at the root of the try and we just go letter by letter. So we would check, like, is P in our try? No, it's not. And so when there's no P, then we can immediately return false. Similarly, for a word like bad, that one's also really easy, right? You just start at the root of your try, and then you would say, like, okay, is B in here? Yes, let's go here. And then is A in here? Yes, let's go here. And is D in here? Yes. And then finally, when we're done with the word, does that word actually, like, is that word a word? It's blue, so yes, it is. So we'll return true there. But the tricky part is how to do the dots. So for like dot add, how would we do that? And pretty much what you got to do for the dot is we're going to actually be recursing, starting at wherever we're at, and we have to check every single path, because this dot can be every single path. Now, there's a few ways you could do this. If you don't want to do it that way, you can actually just make like a list comprehension, or not a list comprehension, but you can make like all possible words starting at the dot, and then you can go through those. So what you could do is you can say, like, okay, instead of actually recursing, let's just like look at what are all the children of my current try, and we'll replace the dot with that. And we have to keep doing that. And if there are more dots, it gets kind of tricky, so I'm not going to do that approach. But essentially, that would be the case. You would make the words beforehand, you would change the dot to like any word possible, and then you could do it that way, right? You can even go, brute force would be change the dot to literally any character A through Z, and just check for all of those words. Okay, so what we're going to actually do for the dot is we're going to try to go through every single path. So like, let's say we try to go through this path here, right? Because the dot is on the root. So we're going to have to try to go to every single path that exists. So let's just say we try to go this path. We try to go to the M path. And then we're going to check for A, and A does exist. And then we're going to check for D, and D does exist. So this is a valid path, and then we do get a word. So if we can go down any path and get the word, then we return true. And actually, any of these paths would work, so it wouldn't really matter. But, you know, let's say it only worked on this path down here, then these two wouldn't work, this one and this one wouldn't work, and then you would just go to the third one, and the third one would work. So essentially, you have to recurse in every single direction from the current try you're at to handle the dot. And that's pretty much it for this problem. For every dot, you have to recurse whatever try you're in. You have to check every single child, and if there's one solution, then you would just return true. So I think we have enough to like actually be coding it now, but that's essentially what we're going to be doing. And the tricky thing is just writing the recursion, but that's pretty much all there is. So let's code it up now. So we don't actually need a constructor because we don't really need any, like, we're just going to initialize some variables to the same thing every time. And we do need to make a try class as well. So let's write it up here. So we're going to say class try. And we also don't need a constructor here. I had a constructor before, but you don't actually need it. So you can just say children is a record. And for the children, it's going to be string mapped to a try. And we're just going to make it an empty object. And similarly, every try has a word that is going to be a Boolean, but we don't need to actually give it a value because we're just going to make it false right away. So this is what every try has. It has a children object mapping the character to new tries, and then a word symbolizing is this actually a word or not. Similarly, for the word dictionary, we don't really need a constructor because we're never going to like take any input. So we're just going to make a root, and it's going to be a new try, and that's pretty much it. This is going to be the variable in the constructor. We don't actually need a constructor, though. If you wanted to, you could make a constructor. Okay. So now add word is pretty straightforward. We just start at the root, and we just go character by character and add it in. And if the character exists, we traverse down. If not, we add it in. So let's do that. So essentially, we just say let node equals this dot root, which is the root try. And then we just go character by character for the word, like in my other previous examples. So for like character of word, if not no.children character, if this character does not exist, let's create it. So not no.children char equals new try. And this is pretty much the same as the other try example. This is all very similar to like insert into try. So now we traverse down into it, and that is essentially all we need to do for the add word, except if we did forget one thing. So once we go through this whole loop, and once we're on some try, we have to mark that try as a word. So whatever node we're on, we have to say node.word equals true, meaning whatever try we're on is actually a word. Okay. So now for this search, we're actually going to add a few more fields to make it easier, because we're going to be doing recursion. So we do have a word. We're going to add a few more things, though. We're going to add an index in the word. It's going to be a number, and we'll default it to 0. So if they don't pass anything, it'll just be 0, meaning it'll start at the first letter of the word. And we're also going to do one more thing, and we're going to pass the current try we're on. So we're going to have a node. It's going to be a try, and we're going to pass on the current try we're on, and we'll default it to the root. And I'll kind of show you why that is. So now essentially we're looping from the character we're on to the end of the word. So initially it's going to be the first character of the word to the end of the word. So we can just say like for let I equals index, I is less than word dot length, I plus. We're looping from the character we're on to the end of the word. So we can actually get this character by saying const character equals word I. So let's get that character. And then we're going to be checking for that dot, right? And this is like the tricky part of this problem. So if the character does equal the dot, then we're going to need to be recursing through every single child in the current try, because every single one of them is a possibility. So then we're going to say for let child in node.children, we're going to recurse through every single one. And we're going to simply like have to figure out like how are we recursing. So we're going to say if. So imagine we're on some character at index I. Like what would we pass in? So we're going to recurse search again, right? But what are we passing in? Well, the word is going to be the same. What index are we going to be at? So if we were at some character I, we're going to want to start at I plus 1, right? We're going to want to start at I plus 1. And then what's the try we want to be on? Well, this is going to be the try that is actually the try we're recursing into. So what's that going to be? That's going to be node.children child, right? We're going to be recursing through all of the children, and then we're going to be trying every single try with the next index. So essentially, that's how you recurse, and this is going to give you every single try that's in our node children, and we will try every single try that we can from our current one. So if this is true, we can just premature return true, because if this was successful, then we can just return true. Otherwise, we keep looping and looping and looping. And if we don't find any of them, then we will return false, because we've tried every single recursion and they all failed. So we can return false. And now the second part is like the normal part. So the second part is a lot more straightforward. So essentially, we just have to check, does that letter actually exist in the children, right? Now it's no longer a wildcard, it's a normal letter. So if it doesn't exist in the children, the way we're going to check is using hasOwn. So we're going to say if not object hasOwn, and this is going to be node.children. So if the node.children doesn't have this character, that means we can't traverse down, so we can return false. Otherwise, the final case is we're just going to be traversing down to the next try. So else node equals node.children char. And so pretty much here, let's go through the logic one more time, right? So if it's a dot, we're going to be checking every single node in the children, and we're going to be recursing into the next index and that nested try. Otherwise, if it's a normal letter, if we can't find the letter in the children, let's return false. Otherwise, we're just recursing into that try, into the next try, right? So we're going into node.children, and we're taking the letter we're at, and we're recursing it to the next try. So if we didn't return here, that means we are currently on a try, and we're done with the word. So then what we have to do is we have to actually check, is the word we're on actually a word? And so here we can just return node.word, not node.word. Yeah, it would be node.word. Because every node has a word boolean that tells you, is it actually the end of a word or not? So you might have recursed down something that might not actually still be a word. Like let's say you have a word ball in your try, but you look for BAL. You would be able to recurse all the way down to that first L, but that wouldn't be a word yet. So then you want to return false here. And I think that's pretty much it, actually. So let's try to run this. And I think it's fine. Or maybe not. So this does give you an error because this is just like, I think they have like an old TypeScript compiler or something where this is like not, I think Hazone is in like ES 2022 or something. So this is just outdated, but this does work. It still runs and stuff. If you don't want to use this, you can also use Hazone property as well, and that would also work. But let's take a look. So it is accepted. And we're getting a wrong answer. Okay. So let's take a look what our issue is. So we try to add A, and then we try to search for dot, which is true. We try to search for A, which is true. Then we try to search for AA, which is false. A is true. Dot A, it says it's true for us, but it should be false. And A dot is correct. So this dot A is a problem for us. So let's take a look in our search and stuff and see what we're screwing up with essentially. Okay, let's take a look. So we have our try, we have our this, that's fine. So we are adding the word. So we are starting at the root and we are going character by character. So that part is fine. And then we are setting it to true. That part is fine. And so for the dot, we are checking the children. Oh, our problem is here. So we didn't actually call this function. We just have a comma. So this needs to be called on this. Okay, now we can try it. We just passed down the function. There we go. Okay, so you can see it's reasonably efficient. So let's talk about the time and space for this one. For each function, I guess. So for add word, worst case scenario, you're going to add the whole word in tries. So for add word, this is going to be O of n, where n is the length of the word. And let me actually check how many dots they can have. So there will be at least most 2 dots. Yeah, because if you have too many dots, this gets really inefficient, and I'll kind of explain why. So for search, essentially we're going to be looping, like when we're going to be going down a try, but for every dot, we're basically multiplying it by 26 because we have to check every single try in the current place, which is going to be 26 characters. So that's going to be something like, since there's only 2 dots, it's not really going to affect it, but it's going to be like 26 squared times the number of characters. So search is going to be O of n because there's only 2 dots, but realistically, if there's 2 dots, it's going to be like n times 26 times 26. Something like that. Which would be, but yeah, since this is the most it can be, since there's only 2 dots. But yeah, essentially, if you wanted to make it, like kind of easier, you would say like, it would be the number of non-dots times 26 to the number of dots. Because every dot means you have to go through 26 unique characters. So now for the space, let's go through that. So essentially, every word you add, you're going to have, let's think, right? Every word you add, worst case scenario is going to be O of n. So add word would be O of n because you would have to like insert a bunch of tries. And then for search, you're not really making new tries. You're more just like, you're reusing one try essentially. So search, I believe, should be O of 1 because we're just traversing. So search, or actually no, there will be a recursive call stack though, right? But it's not going to be, but it's going to be negligible because there's 2 dots max. So the most recursives you can have, like the most levels deep you can have is like 2. So that's negligible. So that's going to be O of 1 space. And yeah, I think that's all for this one. So hopefully you liked this one. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.